Okay. All right. So our last talk of 2020 will be Vander, and he'll be speaking on strategizing and predicting soccer penalty kicks using game theory.
All right. Well, I can't see you guys, but I think it's just gonna have to be that way. So yep, as Dr. K said, I'm Vander, and I will be talking about strategizing and predicting soccer penalty kicks using game theory. So let's see if I can get this. There we go. So my outline for this talk, I'll just first go through a quick background on penalty shots in soccer, and then also game theory and give a brief introduction to that. Next, we will provide a basic game theory model, which is matching penalties game or pennies game. And then from there, we'll manipulate that into the simple penalty game model. We will expand then to the penalty game model from data, which we can use different analysis tools, including comparative game theory statistics and graphical analysis. And then we'll end with the importance of game theory and some possible future work. So soccer is a game that's played with your feet. If you're unaware of what it is, you just try to score in the goal, and that's worth 1 point. If you're fouled inside of the penalty area or the goalie box, as you can see down below, you get awarded a penalty kick, in which one player on the attacking team gets to place the ball in the penalty mark, and they get to take one shot from there to the goal. The only people playing in this scenario is the shooter and the goalie. And so that's what I'll be looking at in my work. Here's an example of what that looks like.
Is this the winning moment? It is! Here I go again, let's at the city.
Okay, so there's just a couple quick examples of what that looks like, if you haven't seen that before. So I can't see you guys, but how many of you guys have played games before or love playing games, sports? If you're in business or economics, I can't see your hands, but I'm assuming a lot of you do enjoy doing those kind of things. Game theory works with those kind of competitive models. It is the study of interacting with choices that two opposing teams have and trying to produce an optimal outcome for each player in those games based on the other's utility. Game theory was first created and formulated by John van Neumann and Oscar Morgenstern in 1944, but this actually goes way back and can date back to Plato even, who incorporates some game theory ideas into a couple of his books, The Symposium and Latus. So here's a very simple game theory model that I will use to kind of explain each part of the model we have going on here. So first you can see that there is a player one and a player two. Player one is the rows and player two is the columns. Each of these players has a strategy. So you can see player one has P1 and P2, and player two has Q1 and Q2. Each of these strategies will produce an expected payoff. So these payoffs are written as A, B, C, D, E, F, and G, and H. So if player one plays P1 and player two plays Q1, we can say they have a payoff of A for player one and B for player two. This expected payoff is the reward that they get from this scenario. So now we will look at the matching pennies game. This is a very simple, basic game theory model that a lot of people have developed already. And this game is just between two children who don't want to do their nightly chores. So they play a game with coins, and each of them takes a coin and flips out or simultaneously reveals their side of the coin. If they are the same, one child wins, and if they're different, the other child wins. So to create a game theory model from this, we first need to determine the payoffs. You can see here that I've already done that. When player one, we'll say, is the same, so they win when the coins are the same, and player two when the coins are different. If the player 1 plays heads and player 2 plays heads, player 1 gets a payoff of 1 and player 2 gets a payoff of -1, which ultimately the numbers don't mean a whole lot except for that one person wins and one person loses. Next, we'll notice that this is a zero-sum game, meaning that for any possible payoff, like positive expected payoff, there's also that in negative. So as you can see, for every 1, there's a -1, which results in a zero-sum game. Next, we can see that it is a mixed strategy game. Basically, what this means is that there are no dominated strategies for each player. A dominated strategy is just a strategy that should be played every single time because it always produces a higher payoff. So if we look at player 1, playing P1 or heads always produces a 1 if player 2 chooses heads and a -1 if tails. However, if player 1 chooses tails, it's not any better or any worse. It's just -1 and 1 again. So this means that there's an optimal strategy that we will be finding for what percentage of the time each player should play each strategy. And lastly, we have to determine the expected payoff. The expected payoff is just if you played this game over and over and over again, what you can expect to have as your payoff. So here we have the optimal strategy equations and the expected payoff equation. Each of these A values you can see is represented in our model down the table to the right. And we'll plug in the values from this model, and we can find that you can see it in the model of 0.5s. Each player has an optimal strategy of 50% for each strategy. This means that the best way for each player to win is to have a random 50% chance for each strategy. And likewise, this produces an expected value of 0. So over the long term, if you played this game over multiple nights and each child doesn't want to do chores every night, each of them will get an expected value of 0, meaning that it'll be an equal chance to do the chores. So the best strategy for this game would be to flip the coin and make it random. So now we can take this and we can manipulate it into the simple penalty game model. So we take our players from here and turn them into the goalies and the kicker. One important thing to remember too is that in soccer for the penalty kick, the kicker is the only one that can have positive payoff. The goalie's best chance is to save the goal and then get a payoff of 0, and they would then give the kicker an expected payoff of 0. And so we can remove the payoffs for when the goalie dives the right way and the kicker shoots that same way. And so we get this model here, and this produces an expected value of 0.5 and -0.5 for the goalie. So what this means would be that 50% of the shots for the kicker are expected to go in over a long-term model. However, if you know soccer, this is a really low number for the kicker and a really high number for the goalie. It's uncommon for the goalie to save half of the shots. The reason for this is that there are a lot of assumptions that go on with this simple penalty game model. Some of those being that the goalkeeper would have to be a superhuman and save every shot if he guesses that direction correctly. This is not the case in real life, but for this model, it was an assumption. Similarly, the shooter would have to be a superhuman in that they never miss the goal and scores 100% of the time when the goalkeeper dives the wrong way. Other assumptions that will actually remain constant throughout the research is that the goalkeeper cannot read the shooter and vice versa. There actually is research that has found that there's not enough time for each of the competing parties to respond to the other's actions. And so we can make this assumption, and that is fair. Another one is that there's no difference in optimal strategy for in-game penalty shots compared to those in penalty shootouts post-game. There are different opportunities to shoot penalty kicks, and I assume they were all the same in this, and that will, again, remain constant throughout the research. So here we will expand now to go to a penalty model based on some data that was collected. A couple more game theory researchers, P.A. Schiapori, Stephen Levitt, and Timothy Grosclose, collected some data from the Italian and French First League shooters, and from 1997 to about 2000. And this data here is the percentage of shots that are scored. So you can see if the goalkeeper dives left and the shooter shoots left, there's actually still a 63.2% chance that the shooter will score. So we can take those values and substitute those in for our payoffs. And we can do that here. So you can see this is our new data-based model. And we will then use our old equations and plug into our values. And here we can see the optimal strategies for each and the expected payoff. So now in this model, we can see that the expected payoff at the very bottom here is for the shooter is 73.8% of the time they should score. And the goalie should only get scored on 73% of the time. So if we put that here, we can see that the goalie should dive left 66% of the time and should dive right 34% of the time. Likewise, the kicker should shoot left 60% of the time and should shoot right 40% of the time. When we're looking at these directions too, one assumption was that the left-footed kickers, it's ultimately just flipped so that they have accurate data. So if you're a left-footed kicker, you can take these numbers and just reverse it. So now to analyze this model, we will use some comparative game theory statistics, which ultimately just lets us put in a variable and see how that variable manipulates our optimal strategy and our expected outcome. So for this example, I chose to see what would happen if the kicker got either better or worse at shooting towards the left, and what would happen if the goalie got better or worse at diving to the right. So that's that X value here. So now we will plug in our values again into these equations, and we find these values, which we'll plug in, which this is a lot, as you can see. So next we can look at how we manipulate X to change the optimal strategies and expected outcomes, but there are very specific cases for X that we need to look at first. First, if X is less than 0.632, we can see that the goalie's right strategy would be a dominated strategy, which means that it always produces a higher payoff than that if the goalie dove left, which would mean that if the kicker got so bad at shooting that they only made 63% of the shots to the right, then the goalie should always dive right. Next, if X equals 0.177, we can see that that substitutes, if we plug that into our equations, you can see that that puts a 0 on the bottom of our fractions. The reason for this being undefined is that 0.177 messes with the zero-sum game aspect of our model, so we have to ignore that value. And lastly, if X is less than 0.44, we can see that for the kicker, just as it was dominated for the right for the goalie, the kicker would then have a dominated strategy to go to the right, because the left would always produce a lower payoff. So if you collect data and find that this is true, then that gives you a dominated strategy, which would mean that you always want to play a dominated strategy. So if we then take these optimal strategies for each player, and we can take the derivative of each of those, we can see that as X increases, P1 decreases. And as X increases, again, Q2 decreases, which means that as the shooter gets better at shooting towards the right, the optimal strategy for the shooter is then to shoot more often to the left, which is very counterintuitive, but that takes into consideration that the goalie might dive to the right more often because you're better at shooting that way. And so then you should start shooting the other way. And similarly, if you're the goalie, as the shooter gets better at shooting to the right, the optimal strategy for you would be to dive left, because just as the shooter would start to shoot left more often, you would also want to start diving left more often so you can save those shots. So now here, we will do some graphical analysis. This graph here is a graph that has the probability of the goalkeeper diving right on the x-axis, and on the y-axis is the expected payoff for the shooter. So when the probability that the goalie dives right is 0, we will put in our payoffs of the goalie diving left at 0. And similarly for 1 when they dive right. And so from 0 to A, we can see that the optimal strategy is for the shooter to dive or to shoot right. Thus the blue line being on top. And then at A, it switches, and the optimal strategy would be to shoot left. So if we know the probability of the goalkeeper diving right, we can make an assumption on what the best option is for the shooter. So we can determine the equations for the lines, and I've done that below, and we can find that A equals 0.344. So now using that number, I took more data that was collected by P.A. Shipori in the same study again, and this data is the observed shots taken. So we can see that the percentage of shots in which the goalie dove right was approximately 41% of the time. And so if we go back, A is 34%. And so because we know that the goalie dove right 41% of the time, it actually is best for the shooter to shoot left, which matches up with our work from before. So that works. So why does this matter? Game theory is very applicable to many fields. Like I was talking about in the beginning, it applies to business, economics, sports, board games, and it uses math. So being an education student, I am constantly looking for different math activities that can apply to our students. Oftentimes, students struggle to find math applicable and feel like it won't apply to their future fields, and they're easy to shut it out. But using this kind of math allows them to see that you can use math for each of these fields and that there is more to it. Similarly, it uses matrices and statistics and is capable of more methods, which all match up with high school curriculum. So I can use these different content strategies all put together into game theory and teach a portion on game theory. So some future work that you can do from this. One thing that I really wanted to do but didn't get the chance is to do a study to collect a large enough sample to create conclusions that are significant for the entire population. The study with P.A. Shipori, they found this data, but they did not find that it was significant for the entire population. I would want to find data that could be applied to all goalkeepers and shooters, instead of having to find data for each specific situation that you might be in to make predictions. Next, I would want to create a game designed for just in-game penalties or for just penalty shootouts or post-game penalties to see if there are different in strategies based on fatigue or other factors that may come into play. And then I would also want to add in the possibility for shooting down the middle, create a matrix where you could have 3 rows and 3 columns. And then if that's possible, then to create and add in the possibility for shooting top, middle, or bottom. This would create a very large matrix that would be very difficult to work with, but I think it would be possible, and that would be an interesting way to extend this research. So these are my, my references. Again, I just used game theory to be able to strategize and predict penalty shootouts. So we can apply that to real life and use that to predict live penalty shootouts and be able to make good decisions about where to shoot if you're taking a penalty kick. Thank you for listening. Does anyone have any questions?
I have a question. What is like the average that a goalkeeper would
I cannot hear that. Dr. Case, could you relay that?
I think the question was, what's a good percentage for saving a shot?
A good percentage is really, so penalty shootouts, we'll say, for example, is just because that's using back to back. Usually, if you save one, possibly two is really good, actually. So if you save 1 out of 5, that's a really, really high percentage. So if with my model, the expected value is actually 75%. So that's saving 1 out of 4. That's actually really, really good. So yeah.
Do you think like the level of play affects your models? Like, would this be quite different with you know, a high school team versus the pros?
Yeah. Oh, for sure. The one thing too is that the assumption that the time it takes for the ball to get from the penalty spot to the goal was based on professional level play. So we could also, I don't think the assumption would be fair under lower level soccer. I think the goalie can make decisions based on the shot, and vice versa. But also, yes, this data was collected by professionals. And so that is why I can't apply this to high school level or even college. I was interested in collecting data and running the same method on my team because I play here at Taylor. So I thought that would be interesting to run that on on our league. But yeah, it would not necessarily bounce around from different levels of play. But if we found that the statistical significance made sense in a future study, then we could use that, but I did not prove that. So
Do you think you could score on a penalty shootout against like one of the top 3 goalkeepers in the world?
I would like to think so. I think I could do it, but I don't know if I could do it consistently. But I've always actually wanted to try that.
Okay. Any other questions? Okay, thank you, Clay.
Yep. Should I just get off or should I stay on?
You should go ahead and get off.
Okay. Thank you.